Mathematical logic is the study of the fundamental principles of reasoning and inference. It provides a formal system for analyzing the validity and logical relationships between statements. This introductory section will cover the basic concepts and notation used in mathematical logic. We'll start by defining what a statement is and how to represent them symbolically. Then we'll look at the different logical connectives that can be used to combine statements. Understanding these building blocks will set the foundation for more advanced logical reasoning. By the end of this section, you'll have the tools to start evaluating the truth and validity of complex logical expressions. Hey everyone! Today we're diving into the fascinating world of mathematical logic. This is like the bedrock of reasoning, how we build arguments and understand if something is true or false. We'll start with understanding proofs. Think of it like detective work, but for math. We'll learn how to use logic to build strong arguments and prove that something must be true. Then, we'll talk about problem solving. Logic is super important for coming up with creative solutions and building powerful computer algorithms. It's like a superpower for tackling complex problems. Finally, we'll explore how logic shapes the world of computer science. It's behind everything from building websites to designing super smart robots. So get ready to unlock the power of logic. Welcome to our journey into the world of logic. It's a super important topic, kinda like the foundation for all the thinking we do. Imagine logic as a special language, one that lets us break down complex ideas and see if they make sense. It's like building a puzzle, where each piece has to fit perfectly. This language is used everywhere. It's how mathematicians prove their theories, how computer scientists build smart programs, and even how philosophers debate big ideas. So, get ready to learn the secrets of this powerful language and unlock your own reasoning superpower. Statements are the basic building blocks of logical reasoning. They are declarative sentences that are either true or false. Symbolic notation is a concise and unambiguous way to represent statements and their relationships using symbols instead of full sentences. Propositions are the core elements of logic. They are statements that can be assigned a truth value of true or false, and can be combined using logical connectives to form more complex arguments. Think of statements as simple ideas or claims you can agree or disagree with, like the sun is hot. Notation is a shorthand way to write down those statements using symbols, making logic easier to work with. Propositions are the Lego bricks of logic. They are the basic building blocks that we can combine to construct more complex logical arguments. This is like the AND operator in computer science. If both statements are true, the whole thing is true. It's like the OR operator. If at least one statement is true, the whole thing is true. This is like saying NOT. If the original statement is true, the negation is false, and vice versa. Think of this as a promise. If the first part is true, the second part must also be true for the whole thing to be true. But if the first part is false, the whole thing is true, no matter what the second part is. This is like saying if and only if. Both statements must have the same truth value for the whole thing to be true. Think of these logical equivalences as shortcuts for logic. They let you rearrange and simplify things without changing the meaning. It's like building with Legos. You can move the blocks around, but the final structure stays the same. The commutative laws are like saying order doesn't matter. You can say, I like pizza and ice cream, or I like ice cream and pizza. It's the same thing. The associative laws are like saying grouping doesn't matter. You can say I have a cat, a dog, and a bird, or I have a cat and a dog, and a bird. It means the same. The distributive laws are like saying you can distribute things. Imagine you want a burger and fries, or a salad. That's the same as wanting a burger and fries, or a burger and a salad. The identity laws are like saying you can't change something by combining it with a really obvious truth or a contradiction. For example, I like pizza and I like food is the same as just saying I like pizza. Alright, let's dive into the world of truth tables. These are like super helpful charts that show you all the possible outcomes of combining simple statements, like it's raining and I have an umbrella. Imagine having a table with columns for each statement and a row for every possible truth combination. By using these tables, we can understand how logical connectives like and, or, and not affect the overall truth of more complex statements. So, stay tuned, because we'll be exploring how to build these tables and use them to solve logic puzzles. Hey there! So, evaluating compound statements is like figuring out if a statement like, I have a dog and it's a golden retriever is true or false. We do this by looking at each part of the statement, in this case, I have a dog and it's a golden retriever, and seeing if they are true or false. Then, we use the rules for and to see if the whole statement is true. Think of it like a puzzle. We break it down into smaller pieces, figure out the truth value of each piece, and then put it all back together to see if the whole thing makes sense. In the next slides, we'll dive into the different types of logical connectives and how they work in compound statements. Get ready for some fun and engaging examples. The goal of this slide is to walk through the 3 steps for constructing a truth table. Step 1 is setting up the table, creating a grid with columns for each variable and the compound statement, and rows to represent all possible truth value combinations. In step 2, we systematically assign t, true, or f, false, to each variable, making sure to cover all possible combinations. Step 3 is evaluating the compound statement for each row, using the rules of logic to determine if the overall statement is true or false based on the assigned variable values. I'll use a step-by-step example to illustrate these 3 key steps in constructing a truth table. Hey there! Ready for a deep dive into logical equivalence? It's like finding 2 different ways to say the exact same thing, even with different words. Imagine it's like finding 2 sentences that mean the same thing, even though they sound different. We'll be using truth tables, which are like logic puzzles to figure things out, and we'll also be doing some algebra with logic symbols. Think of it like a fun math puzzle, but with logic. Let's dive in with an example to see how it all works. Now, let's talk about simplifying logical expressions. Think of it like cleaning up a messy equation. We're going to use a few tricks to make them easier to understand and work with. We'll use rules called logical equivalencies. These are like handy shortcuts that let us rewrite expressions in a simpler way, without changing their meaning. It's like saying I don't like to eat apples is the same as saying I dislike apples. Both mean the same thing, right? Another trick is using distributive laws. Imagine having a bag of apples and oranges. We can distribute them into different baskets, like apples and oranges in one basket and apples or oranges in another. This helps us break down complex expressions into smaller pieces. And finally, we can simplify negations. If you say it is not true, that's the same as just saying it's true. So, we can remove double negations, making things easier to read. Remember, simplifying negations also involves applying them individually to different parts of the expression. Lastly, we'll look for any redundant parts of the expression and remove them. It's like cleaning up your desk by removing unnecessary papers. This makes the expression more concise and easier to work with. Now, let's talk about logical operators. These are like the building blocks of logic statements, and they help us combine and modify propositions. We'll start with conjunction, which is like saying and. It's a bit like a double check, both statements need to be true for the whole thing to be true. Think of it like flipping 2 switches on a light, only when both are on does the light turn on. Next, we have disjunction, which is like saying or. It's a bit more relaxed, at least one of the statements needs to be true for the whole thing to be true. Like choosing between a $1 bill or a $5 bill to get a drink from a vending machine, you've got options. Then there's negation, which is like saying not. It's like flipping the truth value of a statement on its head. If someone says the sky is blue, and you want to negate it, you'd say the sky is not blue. Let's move on to the conditional statement, or if then. Imagine your parents saying, if you clean your room, then you can go out. It's a bit like a promise, if the first part is true, the second part has to be true as well. But if you clean your room and can't go out, that's a broken promise, so the whole statement is false. Lastly, we have the biconditional statement, which is like saying if and only if. It's like making a contract, both parties have to agree to the same thing. For the whole thing to be true, both statements need to have the same truth value, both true or both false. In this example, we'll be taking a sentence and converting it into a symbol-based logic equation. To do this, we need to break down the sentence and understand its meaning. Think of it like turning a regular sentence into a math equation. First, we need to identify the main parts of the sentence, which are called propositions. Remember, a proposition is a simple statement that can be either true or false. Next, we need to assign symbols to each proposition. You can use any letter, but it's common to use P, Q, R, etc. This will make it easier to write and understand the logic equation. Now, we need to use connectives to link these propositions together. These are symbols that represent logical operations like not, and, or, if then, and if and only if. This might seem complicated at first, but it's just like turning a regular sentence into a math problem. By following these steps, you can translate even the most complex statements into a simple and clear symbolic form. In this section, we'll explore the idea of logical validity. It's like figuring out if a puzzle fits together correctly. Think of it as a game of deduction. You have some facts, premises, and you need to see if they lead to a specific outcome, conclusion. We'll go through a step-by-step process to determine if an argument is logically valid. Don't worry, it's not as complicated as it sounds. Ready to crack the case? The slide presents a problem where a student has to choose between studying lecture notes or taking an online practice test. We can represent the student's options as logical propositions P equals study notes, Q equals take online test. We know that studying the notes, P, guarantees a good grade, but it's more work. The online test, Q, is easier but may not be as effective for learning the material. Using logical reasoning, we can determine that the best course of action is to study the notes, P, since that guarantees the good grade which is the student's goal. Logical reasoning allows us to analyze the situation, identify the relationships between the different factors, and make an informed decision. This example shows how logical reasoning can be applied to real-life scenarios to help us make the best choices. Okay, let's dive into solving logic puzzles. These puzzles are all about using logic and reasoning to crack a mystery or figure out a situation. Think of logic puzzles like a detective story. You need to gather clues, analyze them carefully, and use your brainpower to reach the right conclusion. First, we'll break down the puzzle, identifying all the important details. What are the things we're trying to figure out? What are the rules or clues that tell us about those things? And what's the overall goal we need to reach? Next, we'll translate those details into a logical language. We'll use symbols, statements, and connections to represent the puzzle in a clear and organized way. This is like creating a map of the puzzle, so we can follow the clues and connections more easily. Now comes the fun part, applying logic methods. We'll use tools like truth tables, inference rules, and other logical techniques to work through the puzzle's clues and discover the solution. Finally, we'll take our logical solution and translate it back into the puzzle's original language. This means explaining the answer in a way that makes sense, so everyone can understand how we reached the conclusion. Solving logic puzzles is like a mental workout. It challenges your thinking, improves your problem-solving skills, and helps you understand the power of logic.